think we'll be covering k nearest neighbors, right? So let's just step back a bit and see what kind of algorithms we have covered. Uh, and I might be a little bit off here, so that's okay. But we would have started with parametric kind of training algorithms in the supervised learning area, linear regression, and then slowly graduated to maybe L1, L2 ridge and lasso regressions. Then on the classification side, I think you would have covered logistic regression. All these primarily fall under the parametric side of algorithms. Everything have a assumption of the data. That data needs to be in a specific format, not necessarily format, but needs to follow a specific distribution for these algorithms to make meaningful inferences, right? Then we introduced a non-parametric set of algorithms for decision trees, right? And we went on to see how if we combine multiple decision trees, either in series or in parallel, how they form a group of ensemble decision trees, right? Any tree algorithms mostly, or all of them are non-parametric in nature. As we discussed, trees are greedy, maximize the value, can be used for both regression and classification, all of the tree algorithms. That's what we have been covering, right? Now today we'll be spending time on KNN. It's a very simple algorithm, but it's also very important to understand this algorithm because it also opens a window into the bias variance trade-off. And I know there have been some questions on the bias variance in our last class. So I will try to bring in the flavor of bias and variance as we discuss k nearest neighbors today. Okay, and I hope you guys leave with a better understanding of both bias variance trade-off and even k nearest neighbors. Cool. So I think let's start with again a very short story. So Jake is a 3-year-old boy. Okay, Jake is based out of a remote suburb near Paris, France. And as expected, his parents speak only one language, which is French, right? Both his mother and father speak only French. They do not understand English, right? His next door neighbor, who also happens to be a friend, there's a kid in their home. They are also French per se. So they primarily communicate with them in French again, right? And whenever he gets to go to a nearby park or a hiking trail, since it's a tier 3 place out in the outskirts of Paris, primarily he gets people who converse in French, right? As Jake is growing up, it's said again that humans, right, primarily kids, have a capability to learn multiple languages if they are exposed to these languages in their early age, right? Typically when they are younger than 6 or 7 years, right? But as Jake is growing up, he has been exposed primarily to only French, right? So when he grows up, he ends up knowing only French, right? So this is a small story, but now let me quickly add a machine learning angle to it, right? So I hope you guys can see my Jamboard, but what I want to do here is convert this into a machine learning problem quickly. So if I assume that this is the format y equals to f of x, right? And I want to predict that how many languages does a specific kid or any person know, right? How many languages? Yeah. So this is my y, right? And the x that I have is number of, I have only one X by the way, right? Number of languages people in my vicinity speak, or people in my close circle speak, right? I hope the structure is clear. I'm setting this up as a machine learning problem, classification, or sorry, regression problem, where Y is how many languages can a person speak, and on the X there is only one feature, which is number of languages people in my circle speak, right? Now if I put Jake into this equation, the first question is what is the circle here, right? The innermost circle can be parents, right? And I'll just write the number of people here too, right? Maybe if I add neighbors, right? So parents plus neighbors is totally 5. The neighboring family has 3 people, right? Maybe if I add play school friends, or let's say garden friends, right? Maybe it might totally become around 20, because different kids, different families and stuff, right? Now, the feature that we have is this, right? Average number of languages people speak in my circle, right? Jake's parents speak only one language, right? Neighbors also speak only one language. And as we discussed, it's a very suburban area. Everybody just speak only French, right? So it's only one language, right? Now, what I will do is I'll just put in a data point or training data for this, right? Jake was one such example, but it might be that there are many such Jakes or Janes or Michaels or whatever you call it, right? And typically it's again, think of yourself, right? Like just take a moment to reflect. If you know 3 languages, which is very common in India, you will have people in your circle, your family, your very close friends, uh, your family friends, right? They will also be speaking at least 3 or 4 languages. Either that, or you will be one set of family who will be maybe speaking Hindi, other set of family maybe Konkani, depends on where you come from, but typically that's what you will observe, right? So Jake is somewhere here. This is Jake's data point, right? Where all his neighbors or his close circle speak one language, and he also just speak one language, right? But then as more kids, let's say this is a person who is staying in, let's say, Bangalore or Mumbai or Delhi, right? He's been getting much more exposure to multiple languages, right? So in his circle, typically people speak 5 languages, right? And hence he has picked up 4 to 5 languages, right? So this is a very intuitive example of what a person inherits. It's based off the group that you are a part of, or that rubs on of you, right? And this very prominently correlates to the saying that uh, you are sum total of the time that you spend with the top 5 people in your circle, right? Because the kind of energy exchange that happens, the kind of let's say influences you have are primarily driven by those 5 people with whom you spend time with, right? Even though you do not know a specific thing, let's say you do not know cycling, but your close 5 friends know cycling, or if you spend time with those 5 people, or whoever you spend time with most, they know cycling. Eventually maybe either you will learn cycling or you will get interest in cycling, right? So that's how it works, and that's the underlying premise of k nearest neighbors. Okay, now that we have discussed the fundamental, let me quickly introduce slightly more realistic example, right? And we'll go back to the house price to make it easier, right? My y is house price and x is number of bedrooms, right? Let's assume I only have one x feature here, okay? And let's say number 1, 2, 3, 4 bedrooms, right? And it's very obvious that as number of bedrooms increase, the price increases, right? But it's also, we are only considering one feature, so there might be a variability, right? The price range for one bedroom can range between, let's say, I'm just putting some random numbers, but 100K to 400K, right? Maybe this is in an urban area, we do not have those features yet, but let's see, we just have one feature at this point in time, okay? Now, let's just try to apply the concept of k nearest neighbors to this, right? So I will also uh, introduce what k is here as we discuss this example, right? So let's say I want to figure out what's the prediction for this blue colored data point, right? So the first thing that happens in k nearest neighbor is k is a parameter that the algorithm needs to know, right? And as you guys must have anticipated by now, the minimum value of k can be 1 and maximum can be up to number of the samples in the data, right? It can range anything between this, right? So let's say we start with k equals to 1, right? And it's again very intuitive algorithm, right? So if k equals to 1 and if I want to predict what will be the price of the house here, what this does is it tries to take the first closest data point to itself, right? And this is for k equals to 1, right? And the prediction is nothing but whatever value the training data had, right? So this is prediction when k equals to 1, right? I hope in any questions in this prediction when k equals to 1, I'm looking at only one nearest neighbor to predict the price of the house in this case. Okay, I assume no questions so far. Now let's just add some complexity and I'll do k equals to 2, okay? So the moment I do k equals to 2, let's assume this is the second closest data point, okay? And obviously when k equals to 2, even the closest is considered. So I'm considering first distance and the second distance, whichever are the two closest points to this, right? So I have two distances, right? And I will get two values for these, right? So this is one value and this is the second value, right? The predicted value will nothing be the average of these two, right? So pk2 is nothing but the y nearest neighbor 1 plus y nearest neighbor 2 divided by 2, right? And this fundamental stays through, right? If you want to take 5 samples, it will take the 5 here, 5 neighbors, see what's the prediction for them, average out, and that becomes the prediction for the data point that you want to predict it for. Okay. Before pausing, I want to just ensure that the concept is clear by something which is very similar to what I showed, but this is a classification problem. Okay. Okay, what we want to do is there is a gray color dot here, right? And there are two features, right? X is one feature, Y is another, or sorry, X1 and X2 are the two features, right? Y is given by the color, right? So blue is one class, red is the other class, right? I have been tasked to use KNN and determine what's the class of this gray colored or unknown data point, right? This is a observation which I'm expected to score or predict for. Okay. The x1 value for this is 6, x2 value for this is 3, right? So now, as we discussed, the moment I say k equals to 1, what it will do, it will see which is the closest point, right? Which is this specific point, right? Since this is the closest point and this is a blue point, the prediction for this becomes blue, right? What I'm doing, I'm just assigning whatever class the closest point had to this specific unknown class observation, okay? When k equals to 2, let's assume this is the second closest point. There are 2 blues, right? And 0 reds. So again, it will be blue. The moment I do 3, it will still be blue because 2 blues, 1 red, it's still blue, right? The moment I do 4, 3 blues, 1 red, still blue. 5, 3 blues, 2 reds, still blue. 6, 3 blues and 3 reds, right? It will still be blue. And there might be various ways to sort the tie here, right? What's the minimum distance between 2 classes? And in this case, you will find blue. So let's assign blue in this case, right? But now it's interesting. The moment you do k equals to 7, the 7 of the 7 closest data points, 4 are red, 1, 2, 3, 4, and only 3 are blue, right? So the label of the unknown data point turns into a red, right? So I'm predicting now when k equals to 7 that the unknown data point is red, right? I will just take a pause here. What we discussed 2 examples, one on the regression and one on the classification, on what is the logical functioning of k nearest neighbors. So let's take a pause here and see if there are any questions.
Hey, Nayan, I have a doubt here.
Yeah.
So you said that these are based on the predicted values of the nearest neighbors, right? On what basis is that prediction done? Is which algorithm predicts that value?
Okay. So again, there is no algorithm. K nearest neighbor in itself is an algorithm, and I think I know where you're coming from. I hope this should make it clear. Okay. Say I have a training data, right, where I have one y and I have n x's, right, and I have k observations. Okay. For a moment, to make it simpler, I will say this is a classification data set. Just give me a second. This is a classification data set, okay? And this is my training data, right? In my scoring data, right? Let's assume I'm only taking one row, right? And as obvious, since this is scoring, I do not know what the y is. Y is a question mark, but I know the features x1 to xn are known to me. I have some values, right? Now, the way k nearest neighbor works is, if I make it simpler, I make n equals to 2, right? So that I can use a plot like the one we had in the example we are showing. This is x1, this is x2. I plot all my training data points here, right, in red, blue, as we were seeing, right? And let's say this new observation, since I know the axis for this happens to be this point. Okay, so now that I know x1 and x2, I have just plotted this, but I do not know what's the label for this. But for everything else, I know the label. Okay, and it's very similar. Let's say this is red, this is red, this is red, and the rest ones are blue. Okay, very similar to what we saw here. Okay, now the logic is similar. So when k equals to 1, what it does is it tries to find out the closest point. Let's say in this case, this is the closest point. Okay, this is the closest point. So the class is black in this case. Let's say if black and red are two classes. Okay, the class is black because the class for this is black. The moment I do 2, maybe this is the second closest, it's still black. The moment I do 3, it's still black. Right? So there's no algorithm per se, and that's what we will see on one of the salient features of k nearest neighbor. The algorithm is this. Okay, what's the closest data point to me or to the point that I'm trying to score or to predict for? Does that answer your question, Rohan?
Yeah, got it. Yeah.
Any other questions?
So we need to come up with the right set of features for this kind of algorithm, right? Like if some features, even if they are closest, they might not give the correct label. Like we need to come up with a right set of features that will define our correct label, right?
While generically that's correct, what I would like to understand is what do you mean by the right features, right? Because that's true with every algorithm, that you need the right features, and feature engineering plays a very important role. But can you just double click on what's your thought on the right features?
Yeah. Like even if like the features are close enough to the our test data point, it might not be the correct class level. That's what I want to refer to.
Okay. So if that is the case, then even decision trees will falter. Okay, and I can take an example to explain why. See, there is a very again intuitive connection between decision trees and KNN. Okay, while decision trees, it tries to split, right, on variables, right? What KNN does is it tries to use all variables at once using distance metric and tries to directly get at the prediction, right? So let's say if there are two data points, D1 and D2, right, which are close enough, right, in the two features V1 and V2, two variables V1 and V2, right, this will have most likely a incorrect classification even in the case of decision trees, right, because it will have the same decision path for both the data points, but the true label, let's say according to what you're telling, for D1 might be blue, for D2 might be red, right? So you will either misclassify D1 or you will misclassify D2, right? That will also be followed in or captured in distance. But there is one key part which will just come to, which is the distance itself, right? There is a very subtle thing what happens when we combine the variables instead of using one variable at a time. When we use all of them in tandem and define one metric, right, there is one effect that we see, which we will see in a bit. Does that clarify on the question that you have? Yes, it will misclassify that data point, but it will also do it in decision tree or equally affect linear regression as well.
Yeah, does the scale of the features matter while calculate distances
They do,
class level?
they do very much, right? And that's
Like,
the point that will come to in a bit. But any other questions so far on the concept? If no, I think just hold on to that distance metric. We'll come back to that in a moment, okay? And that's very important for us to understand, right? So I think we have discussed most of this. We went through an example, okay? So let's go through some of the key characteristics. I might have covered some of them, but let's quickly go through some of them, right? So KNN is again a supervised algorithm, right? Because we predict a Y in this, right? We need training data for X and Y, so it's a supervised algorithm, right? It belongs to the non-parametric class because there is no underlying assumption or that it makes on the pattern of the data. It's a non-parametric supervised algorithm. Okay. It assumes that previous data point, if there is a good history of data points, even new data points will show us very similar trend. And if you intuitively think, that's true mostly with how humans learn, or most of the machine learning also algorithms also learn, right? Say uh, you guys would have uh, seen some of the or read about the experimentations done on some monkeys, right? That if a specific task is given, if they do the task, you are rewarded, right? So the monkey, based on its history, knows that if I do this task, I will be rewarded, but if I do some other task, I will be penalized, right? So that's the premise of even KNN, that something that has happened in history, and if you give those features again in the future, what the algorithm will predict is, since it's happened in history, that's what will happen in the future, right? It's not well suited for things which drift with time, okay? Patterns that change with time, KNN is not a great algorithm, right? You can apply some constraints on KNN and make it work, but typically if things drift with time, this might not be a good algorithm. As mentioned, this can be used for regression and classification, right? It's again a non-parametric algorithm. It's a lazy learner, right? It's a lazy learner because it does not have a model. It does not do anything, right? The moment you ask it to score, what it does is it goes back to the training data, runs the distance metric with every data point based on what your k value is, and returns the prediction, right? It's a lazy learner, right? And this is also one of the challenges or problems with KNN, that let's say if my historical data has 500 million data points, right? And if I want to now predict for one data point, right? Every time it needs to take the data set with 500 million or whatever that is, compute the distance metric, and based on that make the prediction, right? It's not a great algorithm when you have huge data, right? It's a good algorithm when you have limited data, right? When your features are also lower, and we will see why. This we just discussed. It just uses the training data and classifies based on that, right? So that's KNN for us. Okay. Any questions so far before we get into the distance part? No questions? Cool. Okay. So now the thing with distance, right, is that it's dependent on, or what it is dependent on, it's dependent on number of features, and it's dependent on the scale, right? And both of these are important, and uh, we'll quickly discuss this concept of distance. And let's only take the L2 norm, right, which is the square root, right? And if I have two data points, d1, which is x1 comma y1, and d2, which is x2 comma y2, right? Right. If I want the distance between the two, in L2 norm also is nothing but the Euclidean distance. So this is nothing but square root of x1 minus x2 whole square plus y1 minus y2 whole square. So this is the distance between 1 and 2, right? So the algorithm KNN uses some distance, right? And by default, it is a Euclidean distance to determine what should be the prediction, right? There are options in which you can choose a different distance if need be, but we will use Euclidean distance in this case to for this concept, right? Now let's take a pause here. Can anybody point out what is a major disadvantage of using Euclidean distance, or at least 2 or 3 disadvantages of Euclidean distance? I wouldn't say disadvantage, but challenges or things to keep in mind while using Euclidean distance.
Every feature should be on the same scale.
Okay, so I'll say scale. What else?
It can be computationally expensive when we have too large data.
Okay, computationally expensive. What else? What happens when you have 500 features? Let's say I have 500 features. My data point D1 is represented by, let's say, x1, x2, x3, x4, like that, up to 500.
This is not work in large data set.
Large data set when there are more columns, right?
Yeah.
Why is it so?
Because
Would you be able to?
when we increase the distance of the nearest neighbors, so this might possible to classify clusters.
Okay, fair enough. So third is, let's say, if there are more features, there is an inherent challenge, right? And these 3 things that we have just discussed, right? It's the challenge with Euclidean distance, okay? Not necessarily with KNN. Since KNN uses this by default, it inherits some of these challenges. Now I will use a very simple example to explain the scale part, right? And I think I could not see who pointed out, but scale is a very important thing to keep in mind when working with any algorithm that uses a distance metric, right? It might be linear regression, it might be KNN, and we will even in future see k-means or any hierarchical or any algorithm that uses distance. Scale should be handled, and we are right now focusing on the distance concept. Okay, so let's say I have 2 x's, right? X1 and x2, right? X1 is, let's say, I will say square feet of the house. Let's use the same example, right? And x2 is bedrooms, correct? X2 ranges only from 1 to 4 in my training data, right? Square feet ranges from 300 to 10,000. right? Some farmhouses have very large area. Okay. Now I have two data points, right? This is 2000, 2 and 7000, 4. Okay. The distance between these two, as we discussed, is 7000 minus 2000 square plus 4 minus 2 square under root of that, right? What's this difference? Right? So by the virtue of distance computation, the metric that I'm computing, which is distance, right, is biased, very highly biased to this feature because it has a larger scale, right? A change in this will impact my distance drastically, whereas a change in this will not impact the distance drastically, right? And you will see that, let's say if there are much more data points and if you just work it out in a mathematical way, like taking 69953 or 69952 kind of examples, you will know why this has a lot of impact versus the second feature, right? And especially you will never have just two features, right? Let's say the third feature has a range of 0.01 to 0.10. Okay, so essentially the distance that you will compute there might be 0.01 minus 0.03 whole squared, which again is a different range, right? So the distance will be very biased. Typically Euclidean distance is biased to the ones which have a higher range or the magnitude that is higher, right? Very good practice to always standardize your x's, right? To have the same range. You can do min max scaling, you can normalize the data across mean, anything, right? But or you can do 0-1 scalar, anything, so that the data is in the same scale, so that when you compute the distance, it gives equal weightage to every feature and not because on and not deviates or influenced by the original scale of the data point. Any questions on this concept? This is one of the fundamental concepts which a lot of young data scientists miss while doing a practical implementation. Okay, no questions. Cool. Let's move to the second challenge, which is number of features. Okay. If I have 10 features, right, what's the distance? The distance is, let's say 100 minus 110 squared plus 80 minus, I'm just making these up, okay, plus 65 minus 70 squared plus so on up to, let's say 5 minus, these are not scaled and I just want to show, right? So when you have multiple features and you are trying to combine this, all these features into a single metric, right? In some way, logically, what you are trying to compress the information that your decision tree was taking in multiple steps into just one step, right? That is by using the distance metric. Essentially, if you see, it's doing something very similar. If I take a regression example in a decision tree, the splits are determined, or the variable to split on is determined on what reduces the variance in y value, right? And that's how you split on. And since you're splitting on this side of the data have a specific range in v1, right? And as you go further, the leaves are bounded by similar ranges of the features, right? Intuitively, what you are doing, you're trying to combine all this information into just one metric, right? Which is the distance metric, right? It performs well to some extent, and there is no right answer here when the number of features are typically 10, less than 10, maybe 15, maybe 20, 30. But the moment your number of features increase, the accuracy of what you get from a KNN algorithm also decreases, because this transformation of converting the values or converting the information that a decision tree can capture, a KNN will not be able to convert all that information into a single distance metric, right? So that's the second challenge, or everybody needs to keep in mind that if there are many more features or 100 features or something, KNN is not a good algorithm there. Okay. Any questions? Is it clear on why more number of features, KNN is not a good choice? Fair enough. Third one is, I think we came through the computational feasibility. Yes, I would slightly make it that since it's computing on runtime, right? It's a lazy learner, which means typically what happens in a machine learning model, there is a training data, right? You run a training process, right? Where you create something called as a model object, right? And during scoring, when your new data is coming, all you do is you use your model object and just predict, right? That's a typical, let's say if it's linear regression, decision trees, ensemble models, neural network, anything, you build a model object. This might be stored somewhere in a model repository somewhere or on disk, right? You just fetch that, use that to make predictions, right? In KNN, there is no model object, right? The data itself is used at runtime, right? So when there is a scoring observation, I use the entire data set to make the prediction. And that by the virtue of a lot of computations that have to happen at runtime, it is generally slow in nature. When as your size of the data set increases, or as you have more features, the response time of predictions will increase because it has to do much more computations to respond, right? So these are the three things that we discussed that might be a challenge for K nearest neighbors. Let's take a pause here for any questions.
So, man, one question regarding a Euclidean distance in KNN. So actually, we using a Euclidean distance. So why in a distance between to find out nearest neighbor? So why I'm not using another type of distance like Minkowski and Manhattan distance? Like
You can use that. You can use that. See, even if you use Minkowski distance or a Jaccard distance or Manhattan distance or any distance, right? The fundamental would still remain same. It will help you to overcome some challenges that the Euclidean distance has, but some of the other challenges, right? Like I mentioned that compressing the information into just one metric, that will still remain, right? And that's what is also another point I will not be covering in the session, but that is also a discussion point that can be thought through, that instead of Euclidean distance, use something similar to, let's say, Manhattan distance or a Jacquard distance to compute the similarity, right? And the moment you bring that in, your data can have a continuous variable, a categorical variable, a ordinal variable, etc., etc. As far as you are defining how to compute the Jacquard similarity or Manhattan distance, how does it compute distance, your data set can have any of those features and you will be able to use it, right? While here the mandate again becomes that you need to treat uh, your data set or prepare your data set such that all your features are numeric in nature, right? There are variants, or you can even custom write KNN to work with categorical things, which essentially mean that similar class, which again, see, all of these things converge to using Jacquard or Manhattan distance kind of a thing. It helps to address some challenges, but it does not address everything, because even for, let's say, if I'm using Jacquard kind of a thing, for continuous variables, it will still use a L1 or a L2 kind of a norm. Right? Any other questions?
We saw that
So
like
Nayan,
while calculating the distances, like we give equal weights to all the features. So my
That's
question is
correct.
like how do we calculate feature importances in this model?
Correct. As far as I can logically think, there's no feature importance here. Again, this is again a lazy learner model. There is nothing pre-computed. Typically, feature importance. Uh, Maybe there might be ways in which you can compute, but it's not very logical or intuitive in nature. Like what you could try to do is, uh, what's, let's say, if everything is scaled, right? What you can try to do is uh, difference in each of the x's and the impact of that in y's. You can take these partial deltas and try to use that to come with feature importance. There might be implementations of that already. Somebody would have definitely thought, but you can also custom write it. But I do not see a reason why anybody would want to do that.
so Nayan, could you make one thing clear about KNN? When we are giving one testing data point to our model and giving n equals to 10, so will it calculate the L2 norm for all the will it calculate its L2 norm distance with each training data point, and from that it will select top shortest 10 distances, right? Is it
That's
correct?
correct. That's correct.
Means
That's correct.
it's very lengthy in nature. If I have
Yes.
yeah, millions of rows,
So
then it will calculate
yes,
millions, and then from that it will select top 10.
correct. So
Okay.
I think the way it works is, I think it's there on the screen also. I do not want to read through that, but typically at scoring, what it would do, uh, you have a training or testing observation with, let's say, 10 or let's say 10 features. What I do is, first I compute the distance of this test observation with every observation in my data set, right? I just compute the distance, right? Now, based on whatever the k is, right? K might be 1, 2, 3, 4. So sort these by distances and take the top k, right? Top 10 or top 2 or top 3, right? Then based on its classification takes the max votes, or if it's regression takes the average of y. That becomes the prediction, right? And that's what I think this is just calling that out. Okay, so again, I think we just covered that as the number of rows in the data set increase, this becomes much more computationally intensive, because it needs, every scoring point needs to get to that distance every time at runtime.
Yeah.
So in a regression model also, like suppose I have like some features are there. Suppose in the Boston housing data set. So they will be like similar fashion. They will form clusters here. And then how it works for a regression model? Can you like give some example?
So for a regression model, it's parametric in nature, right? So what does a regression do? Regression does use uh, Euclidean distance or L2 distance, RSS kind of a logic. But let's say I'll just use again x1 and y, right? Y is the price, and let's say x is number of bedrooms or think or square foot, whichever you guys think, right? Let's say if this is the data point, what does a regression do? It fits a parametric distribution to that. So the assumption that I'm making is y and x are linearly related, right? That's the parametric or that's the distribution I'm using. I can choose to use a different form that they are slightly differently related, right? Based on what my understanding of the data, what the EDA shows. But once I choose a form, right, that's the equation that gets used to model a linear regression or a logistic regression or any parametric model, right? When you train on this, what is the output? You get a model, right? In terms of linear regression, what is a model? Y equals to alpha plus beta naught x1 plus or beta 1 x1 beta 2 x2 plus so on, right? Let's make this beta naught, right, till beta n xn, right? So this is the model object, right? When you have to score, all you have to do is just input the x's of the scorings, right? All the betas are determined at the training itself. So the moment you put in x's, it just computes the y and returns. There is no usage of distance metric at runtime. Runtime, it's just a computation of this equation in linear regression, right? This is fundamental difference one. Fundamental difference two is, if let's say, to make it clearer, I am using a linear line, okay? The light blue colored line in this case, right? Irrespective of where my x is, right? The prediction will always lie here for a linear regression, right? By the virtue of how it works. In terms of KNN, it's not that, and we will see that slightly. I think I want to spend 10 to 15 minutes on bias variance using KNN, and this will become clear. But let's say if I want to solve for this point using K nearest neighbor, I will use, based on whatever case, I'll use this. But if I want to solve for this decision point, I'll use this, right? But based on what's the radius of my circle or my k's, right? Typically, when k is small, what will happen is you will predict something like this. Your function will be hugging your data points like the red line, right? You will predict everything correct, right? But the moment your k increases to, let's say, 10, 20, it starts becoming slightly more smooth, right? You're smoothening, and we'll discuss this in detail. But this is the fundamental two, right? That the predictions need not lie on the straight line. There is no model. I'm computing on runtime what the prediction has to be. Okay. Any more questions? I think we have 5 more minutes for a question.
Yeah, Nayan, I was asking actually for last data set, can't we divide the data set into some regions and only find the distance because the k is limited? So find the distance from that region and then make the decision.
Why not? Right. See, that's your art side of your brain, right? You're combining a decision tree logic and KNN logic. It will give you the right answer, but I will question, why do you want to do that, right? Use a decision tree instead and solve for it. KNN is used in a very specific set of use cases, right? Some of the ones that I can think of is that, let's say, when your training data is limited, right? Decision trees typically need slightly more data, right? If you have 100 observations, 50 observations, it will give you some number, but it won't be able to effectively make the splits, because what will happen, your leaf nodes will very soon have less than 5 observations or less than 10 observations, so you won't be able to make deep trees, right? So that's one of the cases where you use a KNN. You want to bootstrap your algorithm. You do not have data, but you want to put something in production. This is a good approach, right? You cannot or the only explanation for a prediction in KNN is that was it happened in the history. My assumption, or what the basic premise for this algorithm is, if it happened in history, it will happen again, and that's why this prediction, right? Previous 10 houses that we saw with the 2 BHK had a price of 50 lakhs to 60 lakhs. That's why any house that we see for a 2 BHK, the price of that has to be between 50 and 60 lakhs. All my prediction is based on the historical data points that I have seen, right?
And if in this case, like if we have 10 clusters, so it will take the average of the 10 prices, like
Yes,
10
it takes the
houses.
average. Yes, it takes the average. So if it's a regression problem, it takes the average of the Y value, and that's the prediction. If it's a classification, it takes the max votes, that let's say 7 are blue, 3 are red. So it assigns blue because blue has the maximum votes. Okay.
So
One
one last doubt.
Yeah,
Sorry.
go ahead.
And like just I have one doubt. Like, then what is the concept of clusters in regression? Like, if there is no such cluster also, then also like I have some data points, I will find the distance and then I will compute the average price. Then, like, I am confused that why cluster is there in regression.
There is no clusters here, and this is not regression, right? That's the second most challenge that a lot of people face. KNN, even by the name, KNN is very similar to k-means. K-means is a unsupervised clustering algorithm. KNN is a supervised algorithm to predict and classify stuff, right? I do not make clusters in KNN. In KNN, what I do, to a observation, you find out what the neighboring observations are and you give a prediction. The premise of predicting is based on seeing the neighbors, right? And then giving a prediction. Clustering is a complete different part. It's more of making observations from the data in a unsupervised way. There is no Y variable in clustering. And I do not know why did you mention regression, but yes, this can be used to solve a regression kind of a problem and a classification kind of a problem. But this is a non-parametric algorithm, whereas linear regression is a parametric algorithm. It
Just
might
like
be,
this.
yeah, go ahead.
So I was asking, like, just like decision trees, KNN is also like bounded.
Yes, it is bounded. Since it's averaged out or max vote, it is bounded.
Yeah.
Okay, cool. Let's quickly cover this and then we will go to.
Name bounded, bounded when when data set is bounded.
Sorry, Prashant, can you repeat your question?
If data set is bounded, then after that KNN is bounded. Okay, whatever K we choose, that is bounded, I think.
No, I think by bounded, what we mean here is the prediction will not go out of what is there in the historical data, right? So let's say if the historical data has house prices from 50 lakhs to 1 crore, right? And you're building a KNN model on this, the the prediction from this model will never be lower than 50 lakhs or never exceed 1 crore, similar to decision trees.
Okay.
But in a linear regression, it might exceed, right? It is
Yeah.
unbounded, right? Because it's a function that you're fitting. Okay, cool. I think advantages of KNN: simple to implement, robust to noisy data. We will see why. Can be effective in training if data is large. Uh, it not necessarily is true, right? That it is helpful, but large is questionable here as to what is large, right? So I would say just ignore this specific point in advantages, right? But it's simple to implement, definitely robust. It can be easily explained, right? Let's say a lot of times you have to explain that why you are giving a prediction, right? So you can always say, but this happened in the history, so I'm predicting this, right? That removes a lot of uh, questions that come back to us, but still we are not able to add in causality or say that, oh, because it has a 2 bedrooms, because it is in a posh locality, it's on 15th floor, the price of this 2 BHK is 1 crore, right? Whereas the other 2 BHK might be on a ground floor in a modest locality and it's 50 lakhs, right? I'm able to assign causality here, but in KNN we will not be able to do that. The answer here will be, boss, we observed 10 historical data points for 2 BHKs with these parameters, and this is my prediction. Okay. It needs to determine K value, which is complex as the data is high, and computation cost is high because it's on the like runtime algorithm. Again, I would say disadvantages: as the data size is high, it becomes slightly higher. Number of features are more, it becomes difficult for KNN to give the right inferences. Okay, cool. Now let's spend some time on, I want to draw some parallels on KNN and bias variance trade-off, right? And this is one of the simplest algorithms using which you can even answer bias variance questions in an interview. Okay, because typically every other model is either, like say linear regression typically has a high bias, right? Whereas decision trees typically has high variance, right? And some of the other algorithms try to balance those out based on hyperparameters, right? Even in decision trees, you can have a model which is high bias, low variance, or low bias, high variance model based on what is the choice of parameters, right? But in KNN, it becomes very easy for us to understand the concept, right? And let's see what that is. Okay. And just bear with me, I need to make some prep to explain this concept. So let's say we'll take a very simple y and x example, right? What I'm doing here is, the first thing that I will do is I will define a true relationship, right? So this is a function, right? This is a true relationship that exists between y and x, and this line I will call, let's say, f, right? So y is related to x like y equals to f of x. Okay. In 100% of the problems that you solve, real life problems, you will not have a true relationship. Okay. You will not know this function, right? If you know the function, your problem is solved. We do not need machine learning to solve or predict the y. I can just apply the function and get the y's. Okay. Let me add some data points, right, from the training data. This might be the true relation, but in actual there might be some noise, some measurement error, some bias, something because of which there is some variances in the data measurement that we have. Okay. It's very clear we are solving a regression problem. So y is continuous in nature and x also is a continuous variable for me. Okay. Let's take a data point which is in red here. Okay. To understand what or how things change as we go from k equals to 1 to, let's say, k equals to 10, right? And it might be evident, we just discussed in the other example on that I was simulating, but this is the k equals to 1, right? That's the nearest number. So my prediction will be this, right? The moment k equals to 2, I use these two, my predictions will be an average of these two, which is this, right? So let me make this red color, k equals to 2. Okay. Let's say if I do k equals to 3, I'll do these three. It will be an average of the 3 data points, right? And I do k equals to 4, I will just add the fourth one, k equals to 4, right? So as my k increases, if you see, the distribution of predictions that I had centers around a specific value, right? If my k is 1, my variance is very high, right? I am very bound to predict a data point which is very close to me, and the moment my closest neighbor changes, my prediction changes, right? What is high variance? My data has a lot of influence on the prediction I make. Okay. As we increase k, what happens? Let's say if I do k equals to 100, right? It uses every data point to make a prediction, right? Every time, no matter what your, here we took this red data point to make prediction or use that. But if I use any other point also, if my k is 100, my prediction will exactly be the same, right? Because what is k, what is the prediction when k equals to 100? It takes the 100 distances, which are every point, take the average, which is just the single point, right? So my prediction will always be this when k equals to 100, right? But when k equals to 1, the prediction might vary, where variance is high, right? Did this difference come through, that k lower k means high variance, right? As k increases, variance decreases. Is this concept clear? Can anybody confirm, or if you have any questions, just ask. Okay, so I'm assuming the concept that when k is low, typically there is very high variance, and as k increases, the variance decreases, and intuitively the bias increases, right? This concept is clear to everybody, right? And let's quickly connect this now with the train and test error a bit so that it's clear. Okay, so we discussed about the true function, right? True function is never known to us. This true function is never known to us, right? I just have these data points with me. What I do is, based on the data that I have, I need to assume, right? So let's assume that if I'm fitting some curve, this is the black is the curve that I have fit, right? This black curve can be very exact, touching every data point, right? Or it can be smooth. I have just drawn two black curves here. One touches every data point and the other one is smooth, right? The one which is touching every data point has very high variance. Let's say this is some model M1, right? This model has very high variance. The other one which is smooth, let's call it M2. This is has lower variance, right? And intuitively, the way you confirm this is, since you know your true function here, you can compute variances, right? Let's say if you remove this data point from the data, right, the impact on variance will be very high. Since you know the true function, you can compute the variance. The impact on the variance error will be very high, right? But if you remove, if you're seeing the high variance model, M1 model, but if you choose the M2 model, even if you remove this data point, the impact will be very low, right? Because it's not fitting every given point, right? It's approximating or smoothing the learning, right? And in this case, there is intuitively, even the smoothened curve very closely resembles the light blue color. So there is a good estimation of the true function, right? Which says that my bias also is on the lower side because I did a good job in estimating my true function. And I'm using a smoothed curve, which is incremental or increasing in nature, right? Think of this now in a KNN setting. KNN exactly works in a very similar way, right? What we discussed in the previous example is very similar, but here I'm explaining in a bias variance kind of a concept. But then the thing is, the moment you vary your case from one and go on increasing, initially your model or your, if it's a classification, your boundary separations will be very random. Let's take that, things will be much more clear. Okay, so let's say I have two classes, I'm solving classification. Okay, just give me a moment here. Okay, now this is the point that I want to predict for, the blue point, right? Now if k equals to 1, right, what will happen? I'm just drawing a decision boundary, right? So I have drawn, even though I've drawn a blue point, but typically there will be a decision boundary, right? Right, so this is for k equals to 1, right? Since blue is here, maybe I should have drawn a red point here to make it, yeah, right? Since blue is here and it's on the right side of the decision boundary, it gets assigned a red color, right? But the moment you use k equals to 10, right, I'm going to a higher number wantingly. Okay, the moment you use k equals to 10, this boundary becomes much more solid, right? Because a point here is using 10 data points close to itself to determine what the prediction is. It might not be a straight line like what I've drawn, but it will be much more smoother than what k equals to 1 was, right? The point here will use the 10 data points closer to this, right? If you use a k equals to 5, it will be in between these two, right? It will be smooth than k equals to 1, but wiggly from k equals to 10, right? And this is, let's say, for k equals to 5, right? In terms of variance, now if we quickly go to variance, k equals to 1 will have very high variance, 10 will have low variance, but has high bias, because what might happen is you might have missed the underlying true function if you are using many data points to predict your data, right? You would have missed that, right? So it might be that you might have a high bias, right? When your k is moderate, and these are relative numbers right now, right? It depends on the data, number of data points, number of features, etc., etc. But when you use a data point in between or k in between, this might be the one where your variance and bias are at the lowest, right? And since we, let's say, know a true function here, I might be able to put in the bias and variance curves. And let's say if this is the total error, sum of the two, I want this specific point, right, where my total error is minimum or my sum of bias and variance is minimum, right? And as if I do not know the true function, I cannot compute. This is a fundamental mistake, or even in interview, right? I do not know the true function in most of the cases, right? Which means I cannot plot a bias variance trade-off curve, right? If it was so simple for us to plot a bias variance trade-off, I need not use the training error and the test error, the cross validation error as proxies for me to figure out, am I overfitting, am I underfitting, do I have high bias, do I have high variance? I can quickly plot this and figure out what is the true situation, right? But I do not know the true function, right? And hence what we do typically, if my train error is very high and if my test error is, oh sorry, if my train error is low and if my test error is very high, right, we assume it's overfitting, right? And if you're overfitting, it might be that you are only using the data from what you have and you're completely missing that, right? And again, based on the kind of models you use, it might be easier to figure out if it's high bias, high variance, and make appropriate corrections for that, so that somehow you reach this point, right? Either by changing algorithms or using more robust variants of the same algorithm, or by using the right parameters in the algorithm, like let's say grow trees deep enough or don't grow trees deep enough, increase the number of trees, etc. Okay, this might be this might get you some questions, so let's see if we have any questions on KNN and how lower k has high variance, and as we increase the k, the variance decreases. Any questions on this?
Hi, Neil.
Yeah.
It's a general question actually. Very many better algorithms there are actually, like random forest and gradient, sorry, XGBoosts and all. So, and KNN, we as discussed, like it is lazy and computationally expensive. So why do we need to study it, or why is it even, it exists if we have such better algorithms? In what case we will, definitely use KNN over those? I want to know that. What would be the case we will choose to use this one first?
Correct. So that's a very valid question, right? And you might find some answers, but I will tell you where I have used, right? There was a case when I had only 37 data points to predict something, okay? And it was very difficult to even fit any model onto that, right? But we had to build something, right? In those cases, when you have less data points, KNN model can be built, right? It uses the historical data and gives you a very realistic model for you to bootstrap till you have, let's say, a good number of data to either fit, linear regression, decision trees, based on what the pattern between y and x is. To bootstrap, this is a good algorithm, right? I have used KNN in another setting, okay? It's slightly controversial if it's right or wrong, but let me explain you the context of that, right? This is in manufacturing where you keep a certain temperature, you keep a certain pressure, and you keep some certain RPM, and the output will have a specific parameters, okay? Some quality of the output, right? So now, in order to predict the final thing, right, it's the relation between these things is a very complex physical, chemical, mathematical equation, right, which is very difficult for you to know, right? So as I mentioned, it's impossible for me to know what's the true relation between, let's say, quality and pressure, RPM, speed, and let's say, I think I mentioned density. Just take some features, right? It's very difficult for me to know the physical equation. Okay? But using KNN, I can easily say, boss, it happened in the past, right? This is an observation, or this is a product that was manufactured on 13th of, or let's say 9th of April, using the same set of parameters, right? And hence I'm predicting it, right? Areas where you do not want to get into the causal side of predictions, right? You are a little bit not ready from a maturity standpoint to explain it to the business yet, right? This can be a very simple explanation.
Okay, sure.
Right? Because
Thank you.
business adoption also is an important aspect when it comes to choice of algorithms, right? If the business is not ready to get in or understand, or if they are very questioning on the inferences and stuff, and you want to start with small till you build up enough infrastructure, data, let's say even resources on machine learning, this is typically one of the algorithms that's used to bootstrap it, right? Other areas where this can be used is a very quick benchmark, right? Or this can be a very good model to make ensembles, right? This gives a very varied range of predictions based on what the K is, right? So you can use this slightly more smarter way to have this in ensembles where you exactly know about that my K equals to 1 will be a very high variance model, whereas my higher K will be a very low variance model. So you might want to use these in a stacking approach. I don't know, it might make sense if you have a lower number of rows there. Okay, cool. I think I hope that was helpful. Let's now quickly move on to the code part. So what we have here is a data set on diabetes where we have to predict a 0 or a 1, right? These are the features: number of pregnancies, glucose, blood pressure, skin thickness, insulin, body mass index, and some diabetes, pedigree function, and age, right? So it's assumed, or based on this data, it's assumed that having diabetes is a function of these parameters, right? And what we are trying to do here is try to fit a KNN model and try to estimate that, right? And I'm again not going to run this line by line, but let's quickly walk through the code. So we are splitting the train test data. There might be imbalanced stuff, and hence we are stratifying. It's always a good practice, even otherwise, to stratify based on Y. What we do here is, since we do not know what the right K value right now is, I'm just randomly taking values from 1 to 8, and I'm building a model for every K value, trying to see what the prediction is. Based on that, I'm computing my train accuracy and test accuracy, right? And I'm just plotting those two things, right? What also becomes evident from this is your train accuracy is very high when your k is 1, because the prediction is always the same point, right? So there's no chance of you going wrong, and as k increases, your training accuracy comes down. With test accuracy, it's the reverse, right? Because not necessarily on an unseen data it has to be the same. So it just gradually increases as k increases and maybe falls down later, right? Which is not very evident here, but we will see now, right? So to summarize, what we are doing here is, since I do not know what k value I should be using, to explain the concept, we run from k equals to 1 to 8 the model for every training data in the training set and the test set, and plot training accuracy and test accuracy, right? Based on this, it might seem like maybe 7 might be a good k right now, right? And that's what we use so far. Okay. There might, and we just plot some classification metrics, ROC, confusion metrics and stuff, right? But now I question myself, why only 7? Why not 18? I have anyways run only till 8, right? Why not 18? Why not 23? Why not 100 Ks, right? It's a very fair question. So then you could put that into a grid search where I say that, okay, I want to run grid search where my neighbors are from 1 to 50. Give me the best neighbor based on cross validation, right? Grid search, we say k equals to 5. So it splits into 5, runs cross validation, tells you that boss, use 14 neighbors. That's giving you the lowest cross validation accuracy, and you can use 14 in your final model. So when you're building a final model, we'll build with neighbors equals to 14. Okay, that was a quick walkthrough of the code. Again, there is nothing that you guys are not aware, or I believe everything here you guys should be aware by now. It's just a different model that we just went through, and so how to implement that in Python. Okay, let's take a moment here and recap. We haven't recapped KNN. So what we started is, we started that KNN by fundamental is that the neighboring people or neighboring data points affect the behavior that I do, right? So essentially, top 5 people who I spend most time with have a high influence on what my behavior is, or what my interests are, what my passion is, right? If I go around a lot with bikers, I will gain interest in bikers, or I have bikers. That's how groups are formed, right? And base that, k nearest neighbor uses that to predict what's my liking, right? So the premise here is, or the assumption that k nearest neighbor makes, that if it's happened in history, it's very likely to happen again in the future, because you are showing those characteristics, right? What we also discussed is, if there is a pattern of time drift, right? Which essentially might relate to that there is some parameter that we do not have the data for, KNN is not a good algorithm, right? Let me take an example here to explain. Let's say in the housing data set itself, right? Let's assume for a moment it took me 3 years to prepare the Boston housing data set, right? I'm collecting data points over 3 years, right? I'm going to every house, asking what's the area, measuring everything, noting the price, right? But over the last 3 years, let's assume the area where I'm measuring this, the temperature has increased quite a lot, right? Earlier, the temperature used to be 20 degrees Celsius, but now it has become 35 degrees Celsius. Let's assume that it has happened, right? Temperature is not a data point I am measuring, okay? So what will happen in the data point that is very recent, when your temperatures are reaching 30, 35, the price of the house will be lower, right? Because nobody wants to stay where the temperature is high, right? But the same house, if you go back 3 years earlier, people will want to buy that house because it's the same house, same locality, but good weather conditions, right? Think of this as another example can be, instead of weather, maybe metro is a good example, right? Metro is being constructed in every tier 1, tier 2 city in India right now. Maybe near my home there wasn't a metro 5 years back. Now there is a plan. In 3 years there will be a metro line, right? But metro is not in my data set, right? But the data point that I measure 3 years back today and 3 years later, the price of the house will be very different, right? And if metro is not a data point, the Y value will show a drift, change in pattern over time, right? Which the data is not capturing. So KNN is not a good algorithm there, right? Typically you see drifts in time series, but even in non-time series data sets, you might see drifts, and you need to be careful if you're using all the parameters, or at least ask questions that what else might be influencing something that the current X's are not able to explain, right? So that's what we discussed. Then we discussed that KNN, or we started with KNN, is a supervised algorithm, non-parametric in nature. It can solve both regression and classification problems. It uses distance as its premise. By default, Euclidean distance. Based on your K values, it uses the nearest neighbors to give the prediction. If it's regression, it uses the average of the data. And if it's classification, it uses the max votes. It's a lazy learner, which means it does not build a model, but what it does is it does predictions in real time, uses the data set, tries to compute the distances, sorts the data set based on the distance, takes the top K and uses that to give the prediction, right? Which by virtue make it very slow if the data set is of high or large number of rows, right? Again, what we discussed, distance, there are two things that we need to be careful about. One, we need to standardize or normalize the data set. Otherwise, what will happen is the features with very high range will impact the decision. The second thing that we discussed is that as the number of features increase, KNN's power of prediction decreases. That's because it tries to compress a lot of information in just one metric, which it might not do a good job at, right? So that are the two things we quickly went through the
So
characteristics.
Henan, so sorry to interrupt. So how we are plotting that separating lines? Means, yeah, that
this line.
yeah.
So this
that
is
boundary.
okay. Assume this is a classification problem, as it's very clear. Assume a hypothetical data point here. Okay. Assume a hypothetical data point somewhere here.
Okay.
Now, I do not know what K is used to plot this, but let's say if K is 6, right? So I assume a data point here, choose K equals to 6 and try to see where does it belong, right? So think of these, you see these smaller data points, like all the dots in the matrix. Yeah. So think that I'm running my algorithm for each of these small points, blue and orange, right? With K equals to 6, right? And every point on the lower side of this line, I'm predicting blue, whereas on higher side, I'm predicting orange. That's why that's how the decision boundary has been come up with.
Okay.
Okay. So again, there is no model, right? It's a simulation based decision boundary that I take this small data point here. Based on what my K is, I try to predict the distance of nearest points and give this a color. And I've just draw the decision boundary based on the predicted color.
Yeah, got it.
Okay. Cool. I think, let me see if I have missed something, right? We have discussed how do we select K, advantages, disadvantages, and Python implementation. Cool. I think we are mostly done with the content of the k nearest neighbors. Let's take a few questions if we have. Maybe we can spend 5 minutes on questions.
Nan, can we say that the observations which lie on the like extreme that have the extreme values of some features that will have a like the model have a greater impact on those observations.
Okay. So your voice was breaking, but what I could understand is extreme observations, right? So what we have said that this is typically robust to outliers, right? It's not necessarily true, but based on what your k is, right? Based on what your k is, I'll use let's say this one to explain. Give me a minute. 8. Okay. Let's say if there is a outlier data point somewhere here, okay, this has a very high value of y, right? It's an outlier in y. Okay, so typically what will happen if there is any point here, I will try to predict a high value for it, right? But the moment I increase my k, right, I'm not just taking this out. Let's say if this is what I'm scoring for, this is the first k equals to 1, my prediction is very high. But the moment I increase my k, I will be increasing my circle and the number of data points, right? So by the virtue of that, I am controlling for outliers as you increase your k, right? Very similar to decision trees as outliers, right? It's still bounded to the range of a decision tree. But what happens in a decision tree, if you allow it to split to the leaf level, like if this leaf has only one observation, this leaf also has one observation, and let's say you draw a decision tree, and every leaf has just one observation, right? What happens here, if something is coming through this decision node, right? If something is coming through this decision node, you are always predicting a very high value. But let's say if you prune your tree, right? If you are stopping here, right? If you're stopping at a higher level, you will average the data points which are there in this node at a higher level, right? This is a analogous example to k equals to 1 to k equals to 5, let's say here, right? It's not apple to apple, but it works in an analogous way in terms of bias variance or overfitting, if I was able to explain this. Does it make sense?
Yeah. Okay.
Any other questions, guys? Okay, so I'm assuming there are, yeah. Yes,
So
Prashant.
when we increasing a k, so maybe possibility model to be underfit na.
If you are increasing your k, your model is underfit. Why do you say so? I'm just trying to understand.
Actually, whatever point are to be coming in all the circle, when we represent all point are to be consistent in a different classifier, and when we train this model, when we test for this, maybe possibility what we thinking in our train that not to be true on test data set.
Correct. So I will not use the word underfit. Yes, it is definitely underfitting, but it's the, if you see on the overfit to underfit, you have not chosen the right uh, uh, right k there. Let me see. I think we had discussed this, right? Where we saw a linear curve when we took a very high K, right? Because every data point is used to make the decision, correct? But when K is lower, like, yeah, I think in this one, what we had discussed, if K is 100, right? I'm using every data point to make the decision, right? Which means my prediction will not change irrespective what the X is, okay? Which means you are definitely underfitting, but in a way that you are not able to, your model bias is very high, right? Your model does not change at all based on the data. Your model has very rigid assumptions or very rigid patterns. It's not able to change. It's very complex. It needs to be slightly more flexible, right? And typically, let's say you lower the K and it starts to become more flexible until you reach K equals to 1, right? K equals to 1 is a very flexible model, right? That's where you start completely overfitting your training data. Did I answer your question?
Yeah, got it.
Okay. Cool.